Hello students, welcome to lecture 9. In this lecture, we will review different linear models that can be used for classification tasks. In the previous class, we studied logistic hypothesis and the gradient descent algorithm. We also derived the gradient of a cross-entropy function in order to minimize the in-sample error of a logistic regression. The outline of today's lecture is as follows. First, we will review linear models for binary classification tasks. Second, we will learn about stochastic gradient descent algorithm, which is a slight extension of the original gradient descent we discussed in the previous class. We will learn about how we can extend binary classification to multi-class classification problems, both for linear regression and binary classification cases. Let's revisit three linear models which use same scoring function: linear classification, linear regression, logistic regression. We have studied all these linear models so far. Here, the linear score is defined as a weighted combination of input features. And the final output, these are the input features, this is the sum of the linear score. And then output, or the final output, or the decision, depends on the type of the function that is used on top of linear scoring function. For instance, in linear classification, we use sine function. While for linear regression, we use identity. We're not doing any change. We're not passing s to any function. In this case, the sine function generates plus or minus 1, depending on the sign of this linear score. In logistic regression case, we use theta, a sigmoid function that squashes this linear score between 0 and 1. Which allows us to link the outputs of our hypothesis to a probability value. We also note that these three linear models different when it comes to the type of in-sample error function used. Right? In linear classification, we used 0-1 error function, and it was discrete in-sample error, non-smooth, not continuous, therefore it is not differentiable. And it is hard to solve, which involves combinatorial quantity. While linear regression, we had squared error function, which is quadratic, convex, and easy to minimize, and also has closed form solution, which is based on matrix inversion. What about the logistic regression? Logistic regression has or uses cross-entropy error function to obtain the optimal hypothesis weights. The cross-entropy function is also smooth, convex, differentiable, and the solution or the minimization of this cross-entropy is obtained using an algorithm called gradient descent. Can we use linear regression or logistic regression to help in linear classification? Because minimizing linear regression is easy due to the quadratic or convexity property of the in-sample error. Logistic regression is also very easy, relatively easy. So that's one of the main questions today we're going to be answering. We can check the relationship of all three linear models and then their error functions again. So all of them use linear scoring function, okay? And then let's consider binary classification problem where the y's or target labels are given by plus minus 1. And let's take a look at the linear classification. So hypothesis h of x uses sine on linear scoring function. And then error is based on this Boolean function, right? H of x, if it's not equal to y, then we count error, pointwise error. H of x, okay, generates sine of the score. So we can change this error function as follows. So error 0-1 error function will take s and then y. From this, we can define classification correctness score. So sine of ys is not equal to 1 is equivalent to the following: sine of s not equal to y. So sine of ys will be correct if the sine of y and then the linear score generates same, let's say, a negative or positive. Okay, if y is negative and the linear score is negative, the sign will be positive. Okay, the sine function will give plus 1, and it will not be equal to +1 then, which means the error is 0. So task here is to maximize, let's call this first YS as a classification correctness score, and then task here is to maximize classification correctness score. And we can rewrite linear regression in sample error function also using the classification correctness score as follows. Error of squared error of S and Y originally uses the difference between S and then Y. Y here is some real valued number, right? So we can change this into YS minus 1 for binary classification. So if Y and then S have the same sign, then it will be positive. And minimizing the squared error is equivalent to maximizing classification correctness score, so that it will obtain 1 or +1, and then we'll have 0 error. Similarly, in logistic regression case, we can also represent cross-entropy function using classification correctness score. It's very simple. So ln 1 plus exponential negative ys. Oh, by the way, the logistic regression in sample error already uses ys, the label of y, so it automatically inherits the classification correctness score. Now we have defined all three error functions in terms of the classification correctness score. Let's try to visualize their graphs. So 0, 1 error function is defined by the following. Squared error, ys minus 1 in terms of classification correctness score. And we also have cross entropy. We denote it as CE, cross entropy, okay, which is equal to the following. And scaled version of cross entropy. Instead of natural log, we are using base 2 log, okay, logarithm. And we call it as scaled cross entropy. Now let's try to visualize all the error functions of three linear models. For example, here we can show the plot of the 0, 1 error function. Okay, here ys is a classification correctness score, and error. Y-axis shows the error. So if you maximize classification correctness score, then 0, 1 error achieves 0. Okay, in the region above this, okay, if ys is higher than 0. While if classification correctness score is small number, then the error will be 1. Now, if you plot the squared error, okay, we obtain the following figure. Let's take a look at it and then try to compare it with the 0, 1 error function. The square error is large if we have ys to be smaller than 1. In this region, if ys falls in this region, then the error will be high. Okay, error will be large. Also, in the following region, if ys is greater than 1, much greater, then the square error will be large. So by comparing these two error functions, we observe that small squared error can lead to small 0, 1 error at the optimal here. So in other words, 0, 1 error is always smaller or equal to squared error in this region. Okay, only equal at 1, but here is smaller. Now we can take a look at the cross entropy. Error function defined as follows, which is here. Okay, this is a graph of cross entropy in terms of ys, and this is output. Cross entropy is a monotonic function, monotonically decreasing function of ys. We can see that as the classification correctness increases, the cross entropy decreases. The small cross entropy error and small 0, 1 error both can converge to a minimum to 0 asymptotically. So this case is different if you compare it to squared error, right? Squared error can only be equal to 0, 1 at 1. We can scale the cross entropy, okay, to link it as a proper upper bound on 0, 1 error function. For example, the scaled cross entropy passes through this point, 0, okay, which is 0 of 0, 1 error function. And then scaled cross entropy can act as an upper bound on 0, 1 error function. For instance, when ys is 0, the cross entropy reaches the 1 and can be used as an upper bound for, let's say, designing an algorithmic error for linear classification as well. Why do we care about upper bound? Since 0-1 error is hard to minimize, the question is, can we minimize different error function that may help in minimizing 0-1 error function? As we have seen in the previous simple visualization examples, we know that for any classification correctness score, and when using linear scoring function, the scaled cross entropy can be a proper upper bound on 0-1 error function, which is equal to 1 over ln2 of original cross entropy function. So minimizing this scaled cross entropy is user-friendly. It's convex and smooth, and also monotonic, function of ys. So if you get the weights by minimizing the scaled cross entropy, can we use the same weights in minimizing 0-1 error function? So we can see the following relation. So in sample error of 0-1 we use for linear classification is has the following relation with the cross entropy. Okay, and we can hope that out of sample error of 0-1 error function will be upper bounded by scaled cross entropy out of sample error function. Also, when we talk about VC dimension of 0-1 error for classification error function, and then VC dimension on cross entropy for the regression, the out of sample error for 0-1 error can be proper upper bounded by in sample error of the same hypothesis plus complexity, which is further upper bounded by the hypothesis that minimize cross entropy plus its model complexity. So out of sample of 0-1 is upper bounded based using the VC theory, in sample error, minimum in sample plus appropriate model complexity, which is itself upper bounded by the following. Okay, so on regression as well, out of sample error of 0-1 error is upper bounded by cross entropy, which is in turn upper bounded by cross entropy plus model complexity of the hypothesis that minimizes this cross entropy. This kind of analysis is useful. That allows us to think about using hypothesis logistic or linear regression, which is obtained by minimizing cross entropy, error or squared error function, since we can show that the small in sample error of cross entropy for logistic hypothesis can also lead to a small in sample error of 0-1 error function. And then we know that both hypotheses use a classification, a linear scoring function. Based on what we have just discussed, we can apply regression for classification tasks, because minimizing in sample error of cross entropy upper bounds on the 0-1 error function. We can use two stages in applying regression for classification. First, we can run logistic or linear regression on your data set with your labels, okay, the binary labels, and then get the weight W, linear regression, for example, or logistic regression. And we can use that weight and apply sign as our hypothesis. All right, so this can be used as our classifier. And if we compare these three linear models again, in other words, the PLA, linear regression, and logistic regression, we know that PLA is efficient, and it provides strong guarantee for minimum in sample error, if, of course, the data is linearly separable. And if data is not linear separable, then pocket heuristic is needed for perceptron. So next, linear regression provides easiest optimization among these three, which we called as also one-step learning, namely which involves inverting a matrix. Okay. However, the cons or the loose linear regression provides loose bound of 0-1 error function when we have large classification correctness score, right? And if you want to use it for classification, you need to keep that in mind. Third, logistic regression provides easy optimization as well, with a good convex in sample error function, okay, which has global minimum and one minimum. The cross entropy function, however, their cons are that the cross entropy is also loose bound of 0-1 error function for very negative Y classification correctness score. We know that linear regression can be useful to set the initial weights for a perceptual learning algorithm, or its pocket version, or even for logistic regression, which involves iterative model selection or iterative hypothesis selection. Okay, and setting these initial weight values using linear regression may be a good starting point for these kind of iterative optimization problems, which will eventually lead to a better or optimal solution much faster, considering the fact that W-lean or can be obtained easier. Also, note that logistic regression is used in most practical classification problems and is definitely preferred over pocket PLA. So logistic regression is one of the popular and then robust classification algorithms that we can use in solving real-world problems. Let's consider two algorithms we discussed before, PLA and logistic regression, or the pocket PLA. Both of them use iterative optimization schemes. For every iteration defined by T, for example, the PLA or pocket PLA or even logistic regression use the following weight update. Okay, we have current weight plus some term that will add to the current weight, which will update to the new weight. And then when we obtain the weight that makes no mistakes and the following term is 0, we return as G. Note that in the PLA, the weight is updated after seeing one example at each iteration. This update is quite fast, and the complexity is O1, big O1 time per iteration. It's quite fast. However, the logistic regression has to check entire dataset and then update WT plus 1. Because the V here, if you remember, is calculated based on the entire dataset and the gradient, gradient of the in-sample error based on the entire dataset. The cross-interpret in-sample error of logistic regression compute the average of the in-sample error for each example in the training dataset. Now the main question is, how can we simplify logistic regression algorithm that uses gradient descent and that will be similar to PLA complexity? Let's revisit the logistic regression algorithm. Here, first we initialize weights, define the loop, iteration, and compute the gradient. This gradient, this is the gradient of the cross-interpret function which we obtained, has to sum across all points. So this summation is time-consuming, And weight update is defined by the following: WT plus current weight minus the following gradient term. If we use gradient descent in this case, the computing cost for each independent variable iteration is of complexity of O(n). So in other words, it grows linearly with the number of training examples, with the n. Therefore, when we train the linear or logistic regression on a large data set, the cost of gradient descent for each iteration will be very high. So we can change, or we can use stochastic gradient descent algorithm that will reduce the computational cost at each iteration. Namely, we want to get rid of this 1/n and summation. But just like PLA, use single example at a time. At each iteration of stochastic gradient descent, we can uniformly sample in one example for data, from data examples at random, and then compute this, the gradient, and update the weight. In other words, we want to move one step at a time using only a single example in the direction of negative gradient, with of course step size defined. So we can think of removing 1/n and the sum as expectation, E over uniform choice of n. So the idea of stochastic descent with random n can be viewed as true gradient with expectation over entire space of gradients. We also know that the stochastic gradient descent inherits randomness. which can be thought of as a true gradient plus random noise. Okay? In the stochastic gradient descent, the main idea is to replace the true gradient by a stochastic gradient, which is computed on a randomly selected sample. And then, after enough computation steps, the average true gradient will approximate the average stochastic gradient. Okay? The stochastic, again, gradient descent is simple and cheaper to compute since it only involves a gradient calculation and then weight update using a single example, which is randomly chosen. PLA uses a single example to update the weight, and then stochastic gradient descent also tries to update the weight based on single example. Right? This algorithm is useful for online learning problems when you have data sequentially coming, or when you have a huge amount of data. However, there are some cons related to stochastic gradient descent, which is related to less stability in nature, because they can get stuck near optimum. However, there are some technique called ADAM, which allows us to overcome this. Now, after removing the averaging and the sum, we can simplify the weight update rule as follows, which moves in the direction of negative gradient, and use it for logistic regression. Let us quickly revisit PLA, perceptron learning algorithm, and compare the weight update rule used there with the stochastic gradient descent, which can be used for logistic regression. The both weight update rule uses one example at a time. Now, PLA uses mistakes to update the weight, and is based on true or false Boolean function. If this is true, okay, then 1, if false, then 0. While stochastic gradient descent uses softer decision. This is our theta sigmoid function when it comes to weight update. And also, this is actually the size of the gradient. So by just looking at these two, we can relate stochastic gradient descent logistic regression as a softened version of perceptron learning algorithm. The connection is clearly seen when PLA can approximate stochastic gradient descent with learning rate eta, and then when we have large classification score, linear classification score. Okay. So now we have two parameters in stochastic gradient descent. One is related to learning rate eta, and then the number of iterations. So there are some practical rule of thumbs in selecting these two parameters. Usually we set the t to be large enough, thousands of iterations. And then eta depends, usually 0.01 or 0.1. Those are the best ranges to select. However, we will learn later the eta can be set adaptively, starting with a large number, large steps, and then going to smaller when the gradient reaches 0. The minimum. Now let's move on to a multiclass classification task, which is another topic in today's lecture. So far we've been talking about binary classification tasks only, which involved learning binary outputs, right? Yes and no, plus minus 1, for example. Now let's ask, how can we solve multiclass classification task that has more than 2 outputs? For example, you want to train a machine learning model to recognize different shapes of images, square, for example, rhomb, triangles, or star shapes as shown here. One possible solution to this kind of multi-class classification problem is to adopt or extend the tools we use so far for solving binary classification tasks. And one possible way to solve multi-class classification problem is to decompose 4-class classification or 4-class data into sequence of 2-class problems. For example, here we can consider one class at a time. Okay, one class at a time. The square or not, okay? We can square or the remaining classes. This can be done by relabeling the remaining class. So we take square as +1 and the remaining rhomb, triangle, and star as -1. Okay, and then we just obtain one hypothesis for solving these binary classification task. In the next iteration, we select romp as one class and remaining the other class, okay? And then obtain another hypothesis. Let's call it as G2, one class at a time. Third, triangle versus the rest. Okay, we're just decomposing 4 into 2, triangle and versus the rest. And we learn this hypothesis. Let's call it as maybe G3. And finally, train a model to classify star versus the rest, okay? And obtain the following hypothesis. We can call it as G4. So at the end of this approach, decomposition approach, we will obtain 4 hypotheses, G1, G2, G3, G4, and can combine them in a way that provides a final decision on a given example, final label. This will form, however, okay, if we combine all of them, hard decision boundary, which looks like a straight line, as you can see, and may lead to an uncertainty, okay, that 2 hypotheses may give the same label to one example, right? So to avoid this kind of situation, we should consider softer decision boundary, or hypothesis that will allow us to provide softer decision boundaries, and which can be obtained using probabilistic functions or hypotheses. We can assume that our hypothesis outputs probability value given an example between 0 and 1, which gives us a softer boundary like this. Okay, the probability of square, okay, for instance, given x is 0.7 versus probability of star given data is 0.75, for example, allows us to select the given hypothesis as a star shape because we have higher probability. Okay, so we're interested in P of star, or shape of them given data. Now we can consider that our hypotheses are all probability distributions and perform one class classification at a time. For example, probability of romp given x. First we estimate this. Next, probability of triangle given x. Okay, we estimate this soft decision boundary. And probability of star given x. Okay, this kind of a softer decision boundary. And after doing that, finally we can combine soft binary classifiers and decide the target label of an unseen example based on the sigmoid output between 0 and 1 if we decide to use sigmoid function as a probability. After learning all 4 hypotheses, we may have 4 different outputs for a given example, and then we select the one with the that maximizes this sigma output with the highest probability for any given example. Select the hypothesis that gives us the maximum of this output, sigmoid output. That's it. So if we summarize one versus all decomposition, this approach uses 2 steps, okay, to solve multi-class classification tasks, which decompose into a sequence of binary problems. For each class K is a class, in our example it was equal to 4, we obtain a hypothesis called WK, okay, or the weight, by running, let's think, logistic regression, okay, which minimizes cross-interval function. And then this step is about relabeling. Given data set, okay, K classes, we label the other majority class as follows. When given y is equal to k, okay, then 2. 2 minus 1 will be 1. And the other, when this is not true, then we will have other examples relabeled as negative 1s. So we are making relabeling or creating pairwise data based on multiclass. And then performing selection of the G based on the one that maximizes the weight. So we can think of this step as efficient, which can be coupled with any logistic regression-like approaches. However, the problem or the cons of this approach is that the unbalanced data, when we have huge number of classes, For example, if you solved 100 class classification tasks, this decomposition will lead to a highly unbalanced data set, where one class having, let's say, 10% of the data, the other class having 90% of the data. Nonetheless, we should keep this one versus all approach as our meta algorithm, and useful for, let's say, for 4-class, 5-class classification problems. We just said that one of the disadvantages of one versus all approach is that it leads to unbalanced data set when we are dealing with multi-class classification tasks that may have thousands of different classes or hundreds of different classes. Okay, let's now ask, can we make data more balanced, or can we have different approaches that allows us to decompose multi-class classification into a sequence of binary classification tasks? One of the approaches would be to decompose the data or multi-class data into pairwise binary classification problems, and then consider not one versus all, but one versus one problem, binary problem. Okay? For example, one versus one problem, we can take only one class at a time. Given 4 classes, just select one class, one pair of classes, this and that. Okay, romp versus square, as shown here. And we ignore or leave out the data from triangle or star shapes and learn the hypothesis just based on these 2 classes of data. Romp, to classify romp, and square shapes. And then iterate. We do the same in the next iteration. We do the same for square versus triangle, while leaving these out, these 2 classes. Next step, consider pair of square and then star shape, and then learn these following hypotheses. Similarly, here as well, we select only 2 classes, romp versus triangle, romp versus triangle. These 2 are left out, and learn the following hypothesis. And finally, romp versus star, romp versus star, triangle versus star, triangle versus star. Once we're done with the training or selecting the hypothesis, we can combine pairwise classifiers. Here we have K classes and K classes L pairwise training examples. Given the following examples, we can see that 1 versus 1 results in more number of multiple classifiers than 1 versus the rest. Okay, the final G will decide the label of the given example using the majority voting rule. Okay? Given one example, if 4 classifiers out of 6 decides one label plus, for example, 1, then it will be +1. Then 2 deciding -1. Okay, so we pass one example through all classifiers and decide final decision as majority vote. It's like tournament champion. To summarize this approach, 1 versus 1 decomposition can be explained in 2 steps. For class K and pair of data L, obtain the hypothesis defined by the following indexes, WKL, by running linear binary classification on the following dataset. Look, this is relabeling or selecting of the dataset. Okay, pairwise data. And then return the G based on the tournament champion. We can note that the following approach is efficient. Smaller training examples, for example. And it is stable and can be coupled with any binary classification approach. However, the cons are, they use the complexity based on PICO K squared for getting the W or the hypothesis. If you have more space, slow prediction, and then more training. Depends on the class, right? So there are 2 different approaches, 1 versus all and 1 versus 1. That allows you to extend the binary classification algorithms to solve multi-class classification problems. So in today's lecture, we have briefly reviewed linear models for classification. Okay? In particular, we were interested in using linear regression or logistic regression weights in solving classification problems, because 0-1 error in linear classification is hard to optimize. And we have reviewed stochastic gradient descent algorithm that uses just randomly one example at a time to perform weight update, and which was followed by examples of extending binary into multiclass classification tasks using logistic regression or binary classification. That's it for today. I'll see you around.